Well, hello there folks, I hope you're doing well. In this video, we're going to be talking about Chapter 15.2, Qualitative Change in Equilibrium Systems. If you're following along in your textbook, this begins on page 690. This is all based on Le Chatelier's principle. So Henri-Louis Le Chatalier was a French chemist, engineer, born quite a while ago, almost 2 centuries ago, I guess, worked in chemical industries and was able to, through a lot of experimentation, learn how to maximize the yield of products in chemical processes. And the results of his experiments created what we called Le Chatelier's principle. So when a system at equilibrium is subjected to a change in temperature, pressure, or concentration of a reacting species, the system responds by attaining a new equilibrium that partially offsets the impact of the change. That seems like a lot maybe to take in, and also there is a little mistake there, but that's fine. I mean, grammatically. Informationally, it's fine. We're going to look at a few different cases, 4 different cases, that show how Le Chatelier's principle is applied in real life. The first one is the change in concentration. So this starts on page 691, a slightly better quality picture, a less grainy picture. Figure 3 you could find in your textbook there. For concentration changes, when you add a reactant to a system that's at equilibrium, it's going to increase the concentration of that substance. I mean, that makes sense. If you have something and add more of it, it's going to become more concentrated. When you do that, if I add more reactant, the equilibrium is going to shift to the right, it's called. It's going to shift toward the products, because if I add more reactants, the system is going to compensate by creating more product. And there will be a large shift at first. Looking at the concentrations, there's going to be a large shift. Obviously, if I add, for this example, I add more hydrogen fluoride gas, there will be an increase in the concentration of the hydrogen fluoride gas. But as time continues on, some of that will react with the carbon tetrachloride, which is liquid and not included in our concentration calculations. And there will be an increase over time of the reaction, or of the concentration of the products, the HCl gas and the CCl2F2, better known as Freon 12 gas. So, so the first one is when we add, increase the concentration of our reactants. The opposite is also going to be true. And I guess if you want to identify this, you'll see a sharp spike in one of them, which slowly goes down, and then a slow rise for your products. If we do the opposite now, so if we, instead of increasing the concentration of our reactant, if we decrease the concentration of one of our products, so in this case, we remove some of our hydrogen chloride gas from the equation, the equilibrium is once again going to shift right to compensate. It's like you're taking something out. It's creating a hole, and so it wants to fill that hole. And so you will have, once again, an increase in your desired product, which is going to be your Freon 12, your CCl2F2. And that's going to occur by reacting more of your hydrogen fluoride. So it's, once again, you see a sharp drop of one of your reactants in this case, and then a less sharp curve of my products and my reactants. The initial Kc value, though, the constant at the K constant. Wow, I've suddenly forgotten the name of it. Our equilibrium constant is going to be the same at the beginning and the end as it will be, for the other one. Because the temperature has not changed, the concentrations themselves don't matter. They are going to find an equilibrium at that constant, always. So the concentrations will be different, but their ratio, based on what we did in 15.1, will be the same. This is used a lot in industrial systems for creating more product. Obviously, they want to get as much product as possible, but it's also super important in your body, especially for the breathing. So those who are in Bio 20, here we go with some more bio once again. So the hemoglobin is, or the place. How do I say this there? So our hemoglobin binding sites, or the oxygen binding sites on the hemoglobin, that's a better way to put it. The oxygen binding sites on the hemoglobin are going to, first of all, take in a lot of oxygen. So they're going to be empty, and there's going to be a lot of oxygen gas. Because of the increase in the concentration of oxygen, the system is going to shift to the right, or we're going to get more of our product, the oxygenated hemoglobin. As the blood circulates through the body, the reactions are going to consume oxygen, and as the amount of oxygen decreases, or the concentration of the oxygen decreases, it's now going to shift to the left, and more of our oxygen is going to be released. So we're going to have an increase in the concentration of our reactants. So in the first part, with a high amount of oxygen, high concentration of oxygen, we're going to have an increase in the concentration of the products. And after a while, we are going to have a decrease in the concentration of the oxygen. So we're going to have an increase in the concentration of the reactants, including the oxygen, because of Le Chatelier's principle. You probably won't have to worry about this, but that's how you're alive, just so you know. The next one that we're going to talk about is temperature change. It's probably easiest to think about temperature change when we write it with the energy in the equation. So, of course, you already know this, but endothermic reactions have energy in the reactant side, or on the reactant side, and exothermic has it on the product side. When we increase the temperature, we are increasing the energy. So depending on where the energy is in our reaction, it is going to either shift it toward the products or the reactants. In, first of all, our exothermic reaction, we have everything at equilibrium. If we increase the temperature, the equilibrium is going to shift to the left. Or in other words, we are going to have a lower concentration, of our products and a higher concentration of our reactant. However, in this picture here, we have a decrease in temperature. So if we decrease the temperature, if we decrease the energy, the opposite is going to occur. It's like, I guess I'll go back to the beginning. If I increase the energy, if I increase the heat, it's like it's expanding. There's no room, so it's going to push it's going to push the reaction toward the left side. However, if I decrease the temperature, decrease that energy, it makes a hole. So it shifts to the right. So I have an increase. If I decrease the energy in an exothermic reaction, I'm going to increase the concentration of my products and decrease the concentration of my reactants, like we see here. So if we've decreased the temperature here, so the SO3 increases in concentration, the O2 decreases in concentration, and the SO2 decreases in concentration. Unlike the first two, where the Kc stays the same because we stay at the same temperature, in this case, the Kc is going to increase if we is going to increase if we increase the energy in an endothermic reaction, and it's going to decrease if we increase the energy in an exothermic reaction. That one's a little tricky to remember. But do remember that the Kc is energy dependent. And unlike other ones, you don't have the huge spikes. It's just you have an equilibrium, and then at the dotted line where all this occurs, it begins another slow shift to a new equilibrium. And once again, there will be a new equilibrium constant from that. Finally, the third kind is if we change the volume. If we change the volume, the Kc value is going to stay the same once again. Our constant will stay the same. However, the equilibrium is going to shift depending on the balance. So, we have to just count how many moles we have on the left and how many moles we have on the right. So in this case, we have 2 SO2 plus 1 O2 yields 2 SO3. So we have 3 moles of reactants and 2 moles of product. So if I increase the pressure by decreasing the volume, so if I make a smaller space, if there's a smaller volume, the pressure is going to increase. When it increases, the pressure will be greater on the side that has more moles. So in this case, the reactant side. And so it's going to shift toward the product side. The concentration of my product is going to increase while the concentration of my reactants decreases. The opposite is also true. If I increase the volume, so decrease the pressure, if I open it up more, it's now going to shift toward the left. Or backward, shift backward, it depends how you want to say it. So the concentration of the SO3 is going to decrease in that case, and the concentrations of O2 and SO2 would increase. Now, if we had another reaction, such as the potassium iodide, which we dealt with a lot in the previous section, we have 1 mole of potassium, 1 mole of iodine, and 2 moles on the other side of potassium iodide. So we have 2 moles on one side, 2 moles on the other side. In that case, when we change the pressure by increasing or decreasing the volume, there will be no change at all. It stays the same. There will be no shift because the the chemical amounts are equal. And adding things to the container, like if I add another gas that isn't going to react, some sort of inert gas like a noble gas, it's not going to change anything either. Or if I have liquids or solids, not going to change anything again, because we only care about, in this case, gases. Aqueous, I assume, would also work, but we don't deal with aqueous, only really with gases. But yes, right, aqueous would matter. We don't tend to deal with that in this. In the practice questions, they do have them though. So once again, finally, let's go to the table. Recap table. First of all, catalyst equilibrium systems. A catalyst changes the rate or the speed that it happens, but doesn't actually affect the overall equilibrium. Great. So our summary. If we increase the concentration, it's going to shift to the opposite side of the increase. So if I increase one of my reactants, the reaction will shift toward the products. If I decrease one of my reactants, it's going to shift toward that reactant. So, adding something to the left will give us a higher concentration on the right. Taking something from the left will add a higher concentration on the left. For temperature, if I increase the temperature, it is going to shift toward the opposite side of the temperature. So if I have an endothermic reaction, for example, where I have energy on the left side of my equation, adding energy is going to increase the concentration of my reactants. whereas decreasing it will decrease the concentration, not decrease the concentration of our reactants necessarily, but it will increase the concentration of our products. So yes, it will decrease the concentration of my reactants. However, it's important to note, perhaps, that despite the fact that increasing the temperature might not actually increase the amount or the concentration of what we desire, most chemical processes are going to occur at a high temperature because it's better to have a lower yield that happens faster than a higher yield that barely happens at all, because increasing the temperature, of course, increases the rate at which everything is moving in the system, increase the amount of reactions, and just increases the overall speed of reactions. Finally, for volume, when we're talking about gaseous systems, of course, because liquids and solids don't matter, if you increase the volume, the side with the higher number of moles is going to be favored, because when you increase the volume, you decrease the pressure, and so things move toward the side with more moles. If you decrease the volume and increase the pressure, it's going to move and favor the side with a smaller amount of moles. Hopefully you're still with me. Hopefully. Let's do a practice question. That's a few practice questions. So we have 5 different formulas here, all different. And it says, which of the systems would shift toward the products with the addition of heat? So the addition of heat, increasing the energy, is going to push or shift toward the side that is opposite the energy. So I have to look for ones that have energy on my reactant side. So this one, number 2, has energy on the reactant side. Number 4 has energy on the reactant side. And number 5 have energy on the reactant side. And so adding energy to these systems will shift the system toward my products. So 2, 4, and 5, that gives me C. C is the answer for the first one. The second one says, which systems, or the systems which would shift toward the reactants with an increase in pressure by compressing the system into a smaller vessel, would be, so when I increase the pressure, the side with more moles loses, or I guess the side with less moles is the one that is shifted toward. So I have to see how many moles I have on each side. I have 1, 1, and 1. So I have 2 on the left, 1 on the right for number 1. So this is going to be a case where increasing the pressure is going to shift it toward my product. So I don't want that. I want to shift toward the reactant. For number 2, I have 1, 1, and 1 and 3. So I have 2 on the left, 4 on the right. In this case, yes, I have a smaller amount. It's going to shift toward the left, the reactant side. So 2 is one of my options. For number 3, I have 2, 1, and 2. So 3 and 2. Once again, it's going to shift toward the product. I don't want that one. 3 and 2, don't want that one. And for number 5, number 4 was 3 and 2 as well. For number 5, I have 1, 1, and 2. So 2 and 2. In this case, it doesn't shift at all. So there is only one reaction here where an increase in the pressure will shift the reaction toward my reactants, and that is number 2. So B is the correct answer. Finally, number 3, it says the system whose equilibrium would not shift because of any change in pressure, and I already talked about this. It's going to be number 5, because I have 2 moles on the left side, or on my reactant side, 2 moles on my product side. And when I have an equal number of moles on each side, changing the pressure does absolutely nothing to the system. And that is it for chapter 15. Hopefully this was clear for you. If you have any questions, please do reach out to me. Let me know. I will try my best to help you out. I hope you have a fantastic day, and I will talk to you later.